Okay, hello everyone, welcome back to the ER model. In the last work, we have briefly introduced the ER model for you already. And in this section, I'd like to provide an overview for the ER model first. So formally, ER model denotes the entity and relationship model. It's used to model the real-world applications. ER model is very simple because we just need to draw some sketches in this model. We don't need to write code. However, it is also very powerful because these basic structures can model the real world about lots of information. And we also briefly introduce the basic structure we can use in the ER model, include these entities. We use this rectangle to represent entities, and we have attributes. We use oval to represent attributes. We have a diamond to represent the relationship, and we also have this triangle to represent the subclass. Inside these basic structures for entity, attributes, and relationship, we can write down their name inside these structures. However, for the subclass, normally the text we can write inside this triangle is fixed. We can write is A, denotes it is a subclass. So I know we can draw the triangle in different ways. For example, we can draw like this. However, we prefer to use this equilateral triangles to represent the subclass. So remember, if you are drawing your ER model, please use shape like this. Don't use something like this, right? It's not good. And we can delete it. So in the next lecture, we also cover how to represent the entities as well as attributes with ER model. And we can also denote the entity has some attributes. For example, we can show a product like this, have a bunch of attributes as shown here. It is similar for components. We can have two attributes as shown here, right? In the next lecture, we also provide the formal definition of relationship. We define the relationship in the ER model based on the product of sets we know from the discrete mathematics. If we still remember the product of sets, it denotes the combination of the elements from these two sets, right? And if set R it is a subset of A times B, then we can define the R to be a relationship between these two sets, right? And we also provide an example of a max as a relationship between product and a component, and we show a bunch of examples in the next lecture as well. So this is what we learned from the last lecture. Okay, so in the last page, we have shown you we can draw some relationships among these entities with this diamond. However, we know in the real world, this kind of diamond is not enough to convey the semantic meanings of such relationships. Because in the real world, between the same sets of entities, we can have different kinds of relationships. They can also illustrate different information. So besides this basic structure, we can cast more constraints on these relationships. We name these constraints as this cardinality constraint. Maybe I can write down the names for you. So for the relationships, we have some constraints. Let me change the font first. We name this one as a cardinality constraint on the relationships. And when we can have more constraints to introduce later in this section on the ER model for you. So as we show in this page, the cardinality constraint we can have for the relationships can be either one-to-one, one-to-many, and many-to-many. And if it is one-to-one, beside the diamond with lines, we can also add one arrow pointing to the entities on both sides, to both the left and to the right hand side. If so, then we can denote it is a one-to-one constraint on this relationship. However, it is one-to-many or many-to-one, then we can add one arrow to one side of its lines and connect to the entities. As to which side we can add these arrows, we can show with some examples as follows. And the third one will be many-to-many. It is a normal case. We can just draw one diamond and connect with some lines. For instance, given two sets of entities, they are the same for all these three cases. We have the one set of entities on the left-hand side is 1, 2, 3, and we have one set on the right-hand side is A, B, C. If it is one-to-one, we can see that all the elements inside the set will be connected by one single link pointing to the other side, right? For both sides. The 1 is connected to B, A is connected to 2, for example, right? If it is many to 1, then for one side of the entities, given an entity, we can find it is connected by one single link, right? Connect to the elements on this side. However, if we look from the right-hand side to the left, given any entity, it can be connected by the multiple links to the left-hand side. So it is different for two sides, right? As to the many-to-many constraints, then generally all the elements on two sides, they can be connected by any numbers of links or relationships with entities from another set. Then the main focus will be for the many-to-one or one-to-many case, how can we show the relationship and which side to add the arrows? Because for many-to-many and one-to-one, it is very simple, right? We know, right? They either have arrows or they don't have arrows. Then the question would be for the one-to-many or many-to-one, these cases, which side we can draw these arrows? We can show you with some examples.